We've seen now several times the satisfiability problem. The input, once again, is a Boolean formula in conjunctive normal form with n variables and m clauses. And the output from the SAT problem is an assignment, a true-false assignment for the n variables, so that the formula evaluates to true. Or we simply output no if there's no such satisfying assignment. Now, as we know, the SAT problem is NP-complete. Hence, we can't hope to find a polynomial time algorithm for the SAT problem. Now, this is a search problem. Let's look at the optimization version. This is the max SAT problem. Now, in the max SAT problem, the input is the same. It's a Boolean formula in conjunctive normal form. And once again, we'll use n to denote the number of variables and m for the number of clauses. The difference is in terms of the output. Even if there's no satisfying assignment, we're still going to output an assignment. And here, we're going to output an assignment which maximizes the number of satisfied clauses. In the optimization version of the SAT problem, we want to find an assignment which satisfies as many clauses as possible. Now, this is still a hard problem. In particular, the max SAT problem is NP hard. It's no longer a search problem, so it's no longer in the class NP, because we have no way of verifying that the number of clauses satisfied is maximum. But clearly, this max SAT problem is at least as hard as the SAT problem. It's straightforward to reduce SAT to max SAT, and therefore max SAT is NP hard. So once again, we can't hope to solve the max SAT problem in polynomial time. Instead, we're going to aim to approximate the max SAT problem. And to do that, we're going to use linear programming. Let's look in detail at what we mean by an approximation algorithm for the max SAT problem. Consider an input to the max SAT, a formula f, where it has m clauses. And let's let m star denote the maximum number of satisfied clauses. So if we look over all assignments to the variables in f, the maximum number of clauses satisfied by any of those assignments is m star. And this is of course dependent on f, so let's denote it as m star of f. Now let's simplify the notation a little bit, and let's drop this of f part. And let's simply denote it as m star, which is the solution to the max SAT problem. Now clearly m star is at most m. If m star equals m, then that means formula f is satisfiable. Now we're going to construct an algorithm which we'll denote as capital A. It's going to take a formula f as input, and it's going to output L on this input f. And to be precise, actually it's going to output an assignment which satisfies L clauses of f. So L is the number of clauses satisfied by the assignment outputted by A. Now how does L compare to the optimal solution m star? Well, in our first instance, we're going to guarantee that L is at least m star over 2. Even though we don't know m star, we're going to guarantee that the output of our algorithm is at least within a factor of 1/2 of the optimal number of satisfied clauses. And if this holds for every formula f, then this is a 1/2 approximation algorithm. And then later in this lecture, we're going to improve 1/2 to 3/4, and we're going to get a 3/4 approximation algorithm for the max SAT problem. And we're going to start by looking at a very simple randomized algorithm. And we'll show that this simple algorithm achieves a 1/2 approximation algorithm for max SAT. After that, we're going to look at an LP-based algorithm. And we're going to prove that this new LP-based algorithm achieves a 1 - 1 over e approximation factor. So it improves the previous algorithm by a little bit. Finally, we're going to look at an algorithm which is a combination of these two algorithms. And this combined algorithm is going to achieve a 3/4 approximation. So let's dive into the simple scheme. Now let's consider some input f to the max SAT problem. And once again, let's denote the variables as x1 through xn. So there are n variables, and there are m clauses which we'll denote as c1 through cm. Now we're going to do the simplest possible scheme for making a true-false assignment for these n variables. We're not even going to look at the formula f. We're simply going to assign these variables randomly to true and false. For each variable xi, independently of the other ones, we're going to set xi to be true with probability 1/2 and false with probability 1/2. So we simply flip a fair coin, and if heads comes up, we set xi to be true, and if tails comes up, we set xi to be false. And we do that for all n variables. Now, how does this random assignment perform? Now, we want to look at the expected performance of this random assignment. How do we measure the performance of the algorithm? Well, we measure the performance by looking at the number of clauses satisfied. Therefore, let W denote the number of satisfied clauses by this random assignment. Now, since the assignment is random, W is also a random variable. Now, since W is a random variable, we want to look at its expected value, which in some sense is the average value of W. In particular, the expectation is the average value of W weighted by its probabilities. Now, what are the possible values for W? Well, the minimum number of clauses we can satisfy is of course 0, and the maximum number is at most m. So let's sum over the possible values. Let L denote the number of satisfied clauses, and L is going to vary between 0 and m. And then we get this value L, and we have to weight it by the probability that the random variable W is equal to L. This is simply the definition of the expectation of a random variable. Now the expectation in this form is quite difficult to analyze. Why? Because whether a particular clause is satisfied or not is related to whether another clause is satisfied or not, because they might have variables in common. Now what we're going to do is we're going to break up this random variable, which is the total number of satisfied clauses, into a clause-by-clause quantity. And in this manner, we're going to be able to analyze each clause in isolation, independent of what happens for the other clauses. And in that way, it's going to be straightforward to analyze the expected performance of the algorithm. So let's look at how exactly we do that. Once again, capital W denotes the number of satisfied clauses for a random assignment. Each variable is assigned true or false with probability 1/2. Now we want to look at a simpler quantity. In particular, we want to look at one clause in isolation. So consider the jth clause, C sub j. And let's make a new random variable, W sub j. Now we're just talking about one clause, so either that clause is satisfied or not. Therefore, this new random variable is going to take either value 1 or 0. It takes value 1 if the clause Cj is satisfied, and it takes value 0 if it's not satisfied. Now what happens if we sum this quantity over all clauses? So we look at the sum for j going from 1 to m of W sub j. Well, we get a 1 for every clause which is satisfied, and 0 if it's not satisfied. So this gives us the total count of the number of satisfied clauses. Therefore, it's equal to capital W. Now recall our original goal was to analyze the expected performance of the algorithm, so we want to look at the expectation of capital W, the expected number of satisfied clauses. Now we can plug in this identity, so we can replace capital W by this sum. So we have the expectation of the sum over j of W sub j, and now recall linearity of expectation. So we can take this sum outside. The expectation of two random variables x and y, expectation of x plus y is the same as expectation of x plus the expectation of y. So now we have that the expectation of W equals the sum over j of the expectation of Wj. Now we can analyze this quantity, expectation of Wj. Notice this just depends on the clause Cj. It doesn't have anything to do with the other clauses. So now we can focus on this clause in isolation. We don't have to look at any of the other clauses. We're looking at this random variable W sub j, which takes value 1 or 0, depending on whether the clause Cj is satisfied or not by the random assignment. We want to analyze the expectation of W sub j. So we take the two possible values weighted by the probability of achieving that value. So we have value 1 times the probability that Wj equals 1 plus 0 times the probability Wj equals 0. Now clearly this term goes away, and we're left with the probability Wj equals 1. This is the beauty of considering a random variable which takes values 0 or 1. The expectation is simply the probability that that random variable equals value 1. Now consider an example of clause Cj. Suppose it's x1 or x2 bar or x3 bar or x4 and so on up to xk. So the clause has size k. Now in order to achieve value 1, the clause has to be satisfied. Let's look at the complement. What's the probability the clause is not satisfied? Now in order to not satisfy this clause, we have to set x1 to false, x2 to true, x3 to true, and so on. There's exactly one setting of these variables, these k variables, so that this clause is not satisfied. The chance x1 is set to false is 1/2. The chance that x1 is set to false and x2 is set to true and x3 is set to true, and so on, so that these k variables are set exactly to this one assignment. The probability of that one assignment is 2 to the minus k. That's the probability that this clause is not satisfied. What's the probability that it is satisfied is a complement of that, so it's 1 minus that. So the probability that Wj equals 1 is equal to 1 minus 2 to the minus k. Now notice something interesting. This gets better as k grows. The worst case is when k equals 1. It's a unit clause. So suppose it's just x1. Then what's the probability this clause is not satisfied is 1/2. And the probability it is satisfied is 1/2. So this quantity is always at least 1/2, since k is at least 1. Now once again, we wanted to look at the expected number of satisfied clauses for this random assignment. we let W denote the random variable for the number of satisfied clauses, and we let Wj denote whether clause Cj is satisfied or not, and then this simplified to a sum over j from 1 to m of whether the expectation of whether clause Cj is satisfied or not. And then we just prove that this expectation, the probability that clause Cj is satisfied, is at least 1/2. This is at least 1/2 for each of these m clauses. Therefore, this whole sum is at least m over 2. So what we've shown is a randomized algorithm which achieves a 1/2 approximation factor, though it's simply the expected performance of this algorithm. Now it turns out we can de-randomize this algorithm. So we can find a deterministic algorithm which is guaranteed to find a 1/2 approximation to the number of satisfied clauses. And this uses the method of conditional expectations. It's quite simple, so let me quickly give you the idea of how it works. So we're going to run through the variables one by one. So let's let I go from 1 to n. Now we're going to try the two possible settings for xi, true or false, and we're going to compute the expected performance for each. So given this setting for xi, and given a fixed setting for x1 through xi minus 1, so the earlier ones are fixed, and now we're trying both possible settings for xi, we compute the expected performance for a random assignment for the remaining variables, xi plus 1 through xn. Now this expected performance is quite easy to compute based on the analysis approach we just did. And what we're going to do is we're going to take the better of these two assignments, and then we're going to fix it, and then we're going to move on to the next variable. Now one interesting feature is that we're not saying something about the optimal number of satisfied clauses. For instance, our formula f might have 12 clauses, and maybe the maximum number of clauses that can be satisfied simultaneously is maybe 10. So m star in this instance would be 10, and m would be 12. Now what we're proving is that a random assignment satisfies at least 6 of the clauses. Now since that's within a factor of 2 of the total number of clauses, therefore we're within a 1/2 approximation of the maximum number of satisfied clauses. And actually what we've shown is that every formula has an assignment which satisfies at least 1/2 of the clauses. Intuitively, if the average is at least m over 2, there must be at least one setting which achieves the average. Now there's one important point that we have to make about the performance of the algorithm, which will be useful later. Instead of max sat, let's consider max exact k-sat. So every clause has size exactly k. For instance, let's consider k equals 3, and suppose every clause in our input formula f had size exactly 3. Now in this case, what's the probability that a particular clause Cj is satisfied? Well, there's one setting of the 3 literals which appear in this clause so that this clause is not satisfied. The probability of that assignment is 1/8. Therefore, the probability that it is satisfied is exactly 7/8. And therefore, for the special case of max exact 3-sat, we achieve a 7/8 approximation algorithm. And what if instead of size 3, every clause had size exactly k? Then the probability that a specific clause is not satisfied is 2 to the minus k. So the probability that it is satisfied is 1 minus that. And therefore we achieve a 1 minus 2 to the minus k approximation algorithm for max exact k-sat. We're going to use later that this algorithm works well when all the clauses are large. And now we're going to make an LP-based algorithm which works well when the clauses are small. Now one interesting tidbit. This 7/8 approximation algorithm for max exact 3-sat is the best possible. Hastad proved that it's NP hard to do any better than 7/8 for this case. If we achieve an algorithm which has guaranteed performance 7/8 plus epsilon for any epsilon, for instance, if we achieve a 0.88 approximation algorithm, then that implies that P equals NP. So this very simple, naive algorithm is the best possible when all the clauses are of size exactly 3. Thus, the hard case is when the formula has varying size clauses. It has some unit clauses, some clauses of size 2, and some clauses of size 3, and so on. But if all the clauses are of the same size, and they happen to be of size 3, then we can achieve the best possible algorithm by just a random assignment. Our second approach will use linear programming to get an approximation algorithm for max sat. To do that, we'll use a stronger form of linear programming known as integer linear programming. Before we get into that, first let's recall the general form of linear programming. Here's a linear program in canonical form. For the variable vector x, we're maximizing C transpose x, subject to the following constraints. Ax is the most b, and x is non-negative. This is the canonical form for a linear program. Now in an integer linear program, so an ILP, it has the same canonical form with one additional constraint. X is constrained to be in z to the n, where z are the integers. So if you think of the vector x of size n, this constraint is saying that each xi is integer valued. So what's going on geometrically? In the linear program, we had a feasible region, this convex set, defined by these constraints. And we're trying to find the best real numbered point, x, in that feasible set, so that we maximize this objective function. But we consider all real numbered points in that set x. Now we're placing this grid, this n-dimensional grid, and we're only looking at the grid points contained in that feasible set. Those are the only feasible points now. And we want to find the best grid point which maximizes this objective function. Linear programming had the nice property that there always is a vertex of the feasible region which is an optimal point, which maximizes this objective function. We no longer have such a property for integer linear programming. And whereas linear programming is polynomial time solvable, so it lies in the class P, in contrast, integer linear programming is NP hard. And we're going to see that right now. We're going to see how to reduce maxsat to integer linear programming. In fact, many of the NP-complete problems that we've seen so far, such as vertex cover, independent set, and so on, are easy to reduce to integer linear programming. So it's a quite powerful technique. Well, since ILP, integer linear programming, is NP hard, we can't expect to solve it in polynomial time. So what's our game plan? Well, first we're going to see how to reduce SAT or maxsat to integer linear programming. Then we're going to look at the linear programming relaxation. So we're going to ignore this one constraint, this integer value constraint. So we're going to look at the best real numbered point, x. Of course, the objective function might go up, but we're going to use this real numbered point x, which is the optimal solution to the linear program, to find an integer point which is nearby. That's going to give us a feasible solution to the integer linear program, and then we'll see how far away it is from the optimal solution. And that'll give us our approximation algorithm to the maxsat problem. We're going to prove now that integer linear programming is NP hard. To do that, we're going to reduce the maxsat problem to integer linear program. Consider an input f for the maxsat problem, and say that f has n variables and m constraints. In the integer linear program that we create, what are the variables going to be? Well, for each variable in the formula f, we're going to add a variable yi to the integer linear program that we create. And for each clause cj, we're going to add a variable zj. So our integer linear program is going to have n plus m variables. And we're going to add the constraints that the yi's are between 0 and 1, and also each zj is between 0 and 1. And since these variables are constrained to be integer valued, they'll either receive value 1 or 0. It can't receive any fractional value. Now intuitively, what's going on? These yi's are going to correspond to whether this variable xi is set to true or false. So yi equals 1 corresponds to xi being true, xi being false corresponds to yi being 0. Zj is going to correspond to whether this clause is satisfied or not. So it's going to take value 1 if this clause is satisfied by the literals appearing in it, and it's going to take value 0 if this clause is not satisfied. That's the intuition. We're going to have a constraint for every clause. Let's take an example clause to get some idea of what we want to achieve. Consider this clause, x5 or x3 or x6. We made all the literals positive in order to make it a simple example. Now what do we want from our constraint? Well, we want that if these variables are set to false, now setting x5 to false is going to correspond to setting y5 to 0, and y3 to 0, and finally y6 to 0. So if these three variables are set to 0, which is going to correspond to setting these variables to false, then this clause is not satisfied. Then we want the variable for this clause to be value 0. So when this clause, this jth clause, is not satisfied, we want this variable zj to be constrained to be value 0. What if it's another setting? Well, then this clause is satisfied. In this case, zj will be value 0 or 1. We can't force it to be value 1. But what we can do is we can try to maximize these zj's. That'll be our objective function. And then the optimal point will take value 1. So if it can achieve value 1, then we will. In summary, the constraint we need to add is that if all three of these variables are 0, then zj is 0. How do we achieve that? We say that zj is at most y5 plus y3 plus y6. So if these three variables are 0, then zj must be 0. Now if at least one of these is 1, then zj can take value 0 or 1. Recall that these variables are constrained between 0 and 1, and also these y's are constrained to be 0 or 1. Let's take a look at another clause that has some positive and negative literals. Consider this clause of size 4, x1 bar or x3 or x2 or x5 bar. Now we want that if x1 is set to true, x3 is false, x2 is false, and x5 is true, which is going to correspond to y1 being 1, y3 and y2 being value 0, and y5 being value 1. Then we want that the variable z for this clause, let's say it's clause j, is forced to take value 0, which corresponds to this clause being unsatisfied. Well, previously when we had just had positive form of these literals, then we looked at the sum of the y's appearing. Now we're going to look at the complement for these negative literals. So we're going to look at 1 minus y1 plus y3 plus y2 because these appear in positive form, plus 1 minus y5 because it appears as a negative form. And we're going to constrain zj to be at most this quantity. So if this setting is true, then zj must be 0. For any other setting of these 4 y's, then zj can be 0 or 1. And in general, for clause cj, we have to consider which literals are positive form and which literals are in negative form. So let's use cj plus and cj superscript minus. Cj plus will of course be the positive literals in the jth clause. In this case it's x2 and x3. And cj minus will be the negative literals. In this case x1 and x5. Now we can look at the general reduction. Consider maxat input little f. Let's define the ILP. Our goal is to maximize the number of satisfied clauses. So we have a maximization problem. For each clause, we have a variable zj, which denotes whether the clause is satisfied or not. It's going to take value 1 if the clause is satisfied, and 0 if it's unsatisfied. So since we want to maximize the number of satisfied clauses, that means we want to maximize the number of clauses where their variable zj equals 1. This sum will be the number of satisfied clauses. Now what are the constraints? Recall we have a variable for each variable in the formula, and we also have a variable in the ILP for each clause in the formula. So let's go over the variables in the formula first. So for I going from 1 to n, we're going to constrain yi to be between 0 and 1. And since this is integer valued, it takes value 0 or 1. Now for each clause, similar constraint, zj takes value 0 or 1. And then we have the constraint for the clause that we just reviewed. So for clause cj, we look at the positive literals. So for each variable which appears in this clause in the positive form, the bad case is when that corresponding variable yi is set to 0. That means that literal is not satisfied. Similarly, for each variable which appears in the negative literal, it's unsatisfied when yi takes value 1, which means 1 minus yi has value 0. And we're going to impose this as an upper bound on zj. So if all the literals in this clause are unsatisfied, then zj is forced to take value 0. So this clause is unsatisfied. And if at least one literal is satisfied, then zj can take value 0 or 1, and since we're maximizing, zj will take value 1 if it can. Finally, we have the constraint that these variables, the yi's and the zj's, are integer valued. So they lie on this n-dimensional grid. Actually, in this case, we're in n plus m dimensions. Now that defines our reduction from maxsat to integer linear programming. In fact, it's equivalent. So this integer linear program is equivalent to the original maxsat problem on this input f. Take this ILP, this integer linear program that we just defined, and consider an optimal point for this ILP. Of course, we don't know how to find this optimal point in polynomial time, and we're not in fact finding it. We're just considering this optimal point for the purposes of the proof. So let y star and z star denote the optimal point for this ILP. Now what's the value of the objective function at the optimal point? Well, the value of the objective function is simply the sum of the z stars. What do we know about the value of the objective function at this optimal point? Well, it equals m star. What is m star? M star is the maximum number of satisfied clauses in the original formula f. M star is what we're trying to find. Now we can't solve this ILP in polynomial time, but we can solve any linear program in polynomial time. Can we convert this ILP into a similar LP? Well, this last constraint is what makes this an ILP. So let's drop this last constraint. So now the feasible points are no longer constrained to be integer valued. And then this changes from an ILP to a linear program. This is simply a linear program now. We can solve this linear program in polynomial time. And let's denote the solution to this linear program. Instead of by y star and z star, let's put the hat there. So y hat star and z hat star are the optimal solution to this linear program. These points we can find. What's the relation between the objective function for the linear program compared to the ILP objective function at the optimal point? Well, the value of the objective function for this LP at this optimal point is the sum of the z hat stars. How do these compare? Well, any feasible point for the ILP is also a feasible point for the LP, because the ILP constrains it to lie on this grid. The LP considers any point. So the LP is considering more points. So, since the ILP optimal point is also feasible for the LP, then the optimal solution for the LP is at least as good as the optimal solution for the ILP. So we know that this objective function value is at least this objective function value for the ILP optimal solution. So we can find an upper bound on the maximum number of satisfied clauses in F. Does that do us any good? Well, not necessarily. That doesn't help us find M star in any way. What we're going to do now is we're going to convert this LP optimal solution into a feasible point for the ILP. It may not be an optimal solution to the ILP, but it will be feasible. How do we do this? Well, we have to convert this LP solution into a point on the grid. The simplest way to do that is to convert these fractional points, these y hat stars, to integer points by rounding them to the nearest integer point. And we're going to do this in a probabilistic way. Now, once we round these to integer points, then we have a valid true-false assignment for our sat input F. And then we're going to prove that this rounded integer point is not that far, not that much worse than the original LP solution, than the fractional solution. And since this fractional solution is at least as good as the optimal integer solution, then we know that the integer solution that we found is not that far off from the optimal integer solution. So we're going to take this LP solution, round it. That'll be worse than this optimal solution, but we'll show that this integer solution that we find is not far off from this fractional solution. So once again, we take this LP and we find the optimal point, and we denote the optimal point by this vector y hat star and z hat star. Hats correspond to LPs, so they might be fractional values. Without the hats, it corresponds to integer. So our goal is to find an integer point. We'll denote it by yi and zj. We drop the stars because it might not be optimal any longer. But we want this integer point that we find by rounding this point. We want this integer point that we find to be close to the optimal integer point. How do we prove that this point that we find, this integer point that we find, is close to this optimal integer point? Because we don't know this point. Well, we show that this rounding procedure doesn't change the objective function too much. So this integer point that we find is close to this optimal fractional point, this optimal LP solution. And this is at least as good as this. Therefore, if this is close to this one, then it's also close to this point. So how do we round from this fractional point to this integer point? Recall our LP and our integer linear program had the constraint that these variables are constrained between 0 and 1. Therefore, this optimal solution also satisfies these constraints, so yi star hat is between 0 and 1. Therefore, we can think of it as like a probability. So we're going to round this. So we're going to set yi to be 1 or 0 with probability proportional to this. So with probability yi hat star, this is between 0 and 1, and it's a real number. With that probability, we set yi to be 1. So if this is 3/4, then with probability 3/4, we set yi to be 1, and with probability 1/4, we set it to be 0. This is known as randomized rounding. Now this actually completes our algorithm. We have an assignment now. We have a true-false assignment for the variables in the original formula. So we've taken this fractional point and we've rounded to an integer point. Notice we don't have to round these z's. We just have to round these y's. Now, if yi equals 1, then we set the variable xi to be true. If yi equals 0, we set the variable to be false. So we have a true-false assignment for the x's. And it's a randomized algorithm for setting these x's. So, as we did before, we want to look at the expected performance of this randomized algorithm. Once again, we want to look at the expected performance of this randomized algorithm that we just defined. Therefore, we let capital W denote the number of satisfied clauses. This is in the random assignment, the assignment produced by solving the LP and doing randomized rounding. Since the assignment is random, capital W is a random variable. So we're going to look at its expectation. Now, to simplify the analysis of the expectation, we're going to do a clause-by-clause analysis. As before, we consider each clause, so we consider the jth clause, and we denote the random variable wj. It takes value 1 if this clause cj is satisfied, and 0 if it's not satisfied. Now, if we sum wj, where j going from 1 to m, then for each satisfied clause we get a count of 1, so the total count is going to be the total number of satisfied clauses, which equals capital W. Now we can analyze the expectation of capital W, the expected number of satisfied clauses, in a manner similar to we did earlier in the lecture. So we can use this identity to re-express expectation of W to be the expectation of this sum. And then we can apply linearity of expectation and take the sum from inside the expectation to outside. So we get that the expectation of W equals the sum over j from 1 to m of the expectation of wj. Now the expectation of wj is quite simple because it's a 0-1 random variable. So the expectation of wj in this case is just the probability that this clause cj is satisfied. Now we're going to prove that the probability that this clause is satisfied is at least 1 minus 1 over e times the LP value for this clause. The LP value for this clause is zj hat star. In some sense, this is sort of like the probability that this LP satisfies this clause, and this rounding procedure, afterwards, this assignment that we end up with will satisfy this clause with probability at least 1 minus 1 over e times this original probability. Now we're going to prove this lemma momentarily, but now let's plug that back into this computation. So we can take this 1 minus 1 over e outside of the sum. So we have 1 minus 1 over e times the sum from j going from 1 to m of zj hat star. Now what is this quantity? This is the value of the objective function for the linear program. What do we know about the linear program versus the integer linear programming? Well, the linear program is at least as good as the integer. So this value of the objective function is going to be at least the value of the optimal for the integer linear program. So this is going to be at least 1 minus 1 over e times this value for the integer linear program. For the integer linear program, it's equal to the max sat. So it's equal to the maximum number of clauses satisfied, which we denoted by m star. And in conclusion, we can show that the expected performance of this algorithm, the number of satisfied clauses in expectation, is going to be at least the optimal number times 1 minus 1 over e. So we're going to be within 1 minus 1 over e of the optimal number, so therefore we have a 1 minus 1 over e approximation algorithm, which improves upon our 1/2 approximation algorithm. So we simply have to prove this lemma, and then we have our algorithm. Let's take a look at this lemma that we're trying to prove. Look at a clause cj, and let's say cj is of size k. And let's suppose the clause is x1 or x2, and so on up to xk. So we're assuming all the literals are positive form. Let's just do the analysis for this simpler case, and the same approach will apply to the general clause. And in fact, since we're just looking at this clause in isolation, and because of the symmetry, we can always convert this clause to appear in this form. Now, what was the LP constraint for this clause? Let's look at it in terms of the optimal solution to the LP. So variable x1 has this variable in the LP, y1 hat star. We want that if this is 0, meaning x1 is false, and if that's the case for all k of these variables, then we want that this variable zj hat star is 0 in this case. So if all these literals are unsatisfied, meaning all these variables are set to false, then all these y's are set to 0, then zj must be 0, corresponding to this clause being unsatisfied. This is the LP constraint. Now we're trying to analyze the probability that this clause is satisfied after the randomized rounding procedure. This is of course the same as 1 minus the probability that this clause is unsatisfied. What's the probability that this clause is unsatisfied? Well, what's the probability that all of these variables are set to false? So we're going to look at the product over these k variables. The ith one is set to false with probability 1 minus yi hat star. Now if you recall the lemma, we're trying to show that the probability that this clause is satisfied is at least 1 minus 1 over e times this quantity, zj hat star. What we know is that the probability it's satisfied equals 1 minus this product of these yi's. Now we know how to relate the sum of these yi's to this zj star. How do we relate the product to the sum? So we want to relate this product to this sum, and then we can relate it to zj hat star. To relate this product to this sum, we're going to use the geometric mean, arithmetic mean inequality. Let's take a look at the arithmetic mean, geometric mean inequality. Let's take a look at its general form. We have k non-negative numbers, w1 through wk. Think of these as weights. We want to look at the mean of these weights. So we can look at the arithmetic mean and the geometric mean. The arithmetic mean takes the sum and divides by the number of terms. The geometric mean takes the product and takes the kth root. How do these two things relate? Well, the arithmetic mean is always at least the geometric mean. And this holds for any non-negative weights. Now how do we relate this to our problem? Well, we're going to set wi to be 1 minus yi star hat. And then the arithmetic mean is 1 over k times the sum of 1 minus yi hat star. And this is at least the geometric mean, which is the product over I of 1 minus yi hat star. And then we take the kth root of the right-hand side. Now alternatively, instead of taking the kth root of the right-hand side, we can take the kth power of both sides, and we have the following inequality. This is the one we're going to use. Going back to our analysis from earlier, we're looking at the probability that this jth clause is satisfied. This equals 1 minus the probability it's unsatisfied, which is the product over I from 1 to k of 1 minus yi hat star. Now we can apply the arithmetic mean, geometric mean inequality. Now we can apply the arithmetic mean, geometric mean inequality. The arithmetic mean is 1 over k times the sum of I going from 1 to k of 1 minus yi hat star. And then we're raising it to the kth power, since we dropped the 1 over kth root of the geometric mean. Now the inequality said that the geometric mean is at most the arithmetic mean, but we're doing negative of this, so we get that it's at least. Now we can simplify this a bit. We can do the sum over each of these terms separately, and the first term is a sum over I from 1 to k of 1. That's simply k. So that divides by this 1 over k. So we get 1 for the first term. So we get a 1 for this first one. And the second term becomes 1 over k times the sum over I from 1 to k of yi hat star. And then we get this whole quantity raised to the kth power still. Okay, now we're in business because we have this sum over these yi hat stars. Now if you recall before, we had this constraint from the linear program. It said that if each of these variables was set to false, so each of these y's was set to 0, then the corresponding zj must be 0. Now this is actually a linear program, so we don't have these integral constraints. So we simply know that the sum of these y's is at least this real number z. But we still have this inequality, and our goal is to relate this probability that this clause is satisfied to this quantity zj hat star. So we can apply this inequality, plug it in, and we can drop these y's and get the z. Now this is a least, then we're doing a negative, and then another negative. So we get that this is at least 1 minus the quantity 1 minus zj hat star over k, all raised to the kth power. So we replace this sum over y's by zj hat star. Now we have to do a bit of calculus to simplify this. What we want to do is we want to move this zj outside of this kth power. So let alpha denote zj hat star. What we've shown so far is that the probability that this clause cj is satisfied is at least 1 minus alpha over k to the k. Now once again, we want to get this alpha outside of this power. We want to make it a linear function of alpha. So let's look at this function of alpha. Let's define f of alpha to be this right-hand side. And our claim is that f of alpha, so this right-hand side here, is at least some constant times alpha. Now it's a constant in the sense it's independent of alpha. It does depend on k, the size of this clause. Now what is that constant there? Well, it's going to be similar to this without the alpha. It's going to be 1 minus quantity 1 minus 1 over k raised to the kth power. Once we prove that, then we can apply that here, and we get that this is at least this quantity, which is this constant, times alpha. So we got the alpha outside of the power. So it's now linear in alpha. It's linear in this z. Now how do we prove this claim? Well, first off, you take the second derivative and you prove that it's negative. Therefore, this function is concave. Now, since f of alpha is a concave function, it's going to look something like this. Now we're trying to relate f of alpha, this curve, to this linear function. Let's denote this linear function as beta alpha. So this quantity here is beta. Now let's look at this line beta alpha. Now for large values of alpha, it might not be bigger. But notice, what values of alpha are we interested in? We're interested in alphas between 0 and 1. So we only need this claim for values of alpha between 0 and 1. So since it's a concave function, it's got one peak. So if we look at the endpoints that we're interested in, 1 and 0, and if we prove that this curve is above this line at these 2 points, 0 and 1, then it's also above at every intermediate point. So once we take the second derivative and prove it's concave, then it suffices to check the point 0, alpha equals 0, and alpha equals 1. And if you plug in alpha equals 0, we get 0 on both sides, and alpha equals 1, it's straightforward to check that that's also true. Okay, we're almost done. Actually, we really are done. We just have to summarize. We're looking at the probability that this clause Cj is satisfied. This equals 1 minus the product over I of 1 minus yi hat star. Then we applied the AM-GM inequality to convert this product into a sum. Then we applied the LP constraint to relate that sum over the yi's to zj. And then we got this inequality. We got that this is at least 1 minus the zj hat star over k raised to the kth power. Now what we just proved is that this whole thing is at least this constant, which is a function of k, but independent of z, 1 minus the quantity 1 minus 1 over k to the k, times zj hat star. Okay, now let's simplify this a little bit. If you recall the Taylor series for e to the minus x, it's 1 minus x squared over 2, x cubed over 3 factorial, and then plus minus, alternating series. Now what if we want to relate e to the minus x to 1 minus x? Well, the next term is positive, so e to the minus x is going to be bigger. So 1 minus 1 over k is at most e to the minus 1 over k. Raised to the kth power, we have 1 over e. And then take minus, and then we have it's at least. So we have this quantity becomes 1 minus 1 over e times zj hat star. And that's what we wanted to prove. That was the lemma we claimed. And therefore, we have a 1 minus 1 over e approximation algorithm. That completes the analysis of this LP-based algorithm. Now let's summarize some important points about this LP-based algorithm. It's a very general approach. We can take a hard problem, and oftentimes we can reduce it to integer linear programming. Integer linear programming is very general, very powerful technique, so it's very common that we can reduce these NP hard problems to integer linear programming. Then we can relax it to a linear programming. We just drop this integrality constraints, and then we can solve it. There are polynomial time solvers, though we can often use simplex algorithm. It's often fast. Then we can take this LP solution and we can round it in some randomized way, as we just did for its SAT. And this gives us a feasible point for the integer linear program. And hopefully it's a reasonable heuristic for the solution, the optimal value of this ILP. Now we've seen two algorithms for max SAT. Now what if we look at max SAT on exact k-SAT formulas? So these are formulas where all clauses have size exactly k. And let's look at the performance of these two algorithms we've seen so far as a function of k. So we have the simple algorithm. That's the simple randomized assignment. So each variable is set to true with probability half and false with probability half. And we have this LP-based scheme. So we write max SAT as an integer linear program. We relax it to a linear programming, and then we round it. How do these two schemes compare for different values of k? Let's take a look. Let's look at the performance of these two algorithms for k equals 1, so it's all unit clauses, so it's quite trivial, k equals 2, and k equals 3, and in general k. If we recall the simple algorithm, the probability a clause is not satisfied is 2 to the minus k, So the probability it is satisfied is 1 minus 2 to the minus k. So in general for k, it achieves a 1 minus 2 to the minus k approximation factor. Plugging in k equals 1, we get 1/2. K equals 2, we get 3/4. K equals 3, we get 7/8. Now the LP, the general form, was quite complicated. We proved for general k that it achieves 1 minus the quantity 1 minus 1 over k to the kth. Plugging in k equals 1, we get 1, which is quite good. The simple scheme was quite bad for k equals 1, but the LP-based scheme is quite good. At k equals 2, they match, both 3/4. For k equals 3, we got 1 minus 2/3 cubed. If you plug that into a calculator, that's roughly 0.704. So for k at least 3, the simple scheme beats the LP scheme. But for small clauses, the LP scheme is at least as good or even better. The key observation is that if you look at each row, the max in each row, the best of these two schemes for every k, is at least 3/4. So can we combine these two schemes to achieve a 3/4 approximation? Yes, we can. Here's our combined algorithm. Take our input formula f. We first run the simple randomized algorithm, which assigns each variable true or false independently with probability 1/2. And we get an assignment which satisfies, let's say, M1 clauses of f. So M1 is the number of clauses satisfied by this simple algorithm, the simple randomized algorithm. We also run the LP-based scheme, and we get an assignment. We look at how many clauses are satisfied by that assignment. Let's say it satisfies M2 clauses. And whichever of these two is better, we take that assignment. So we look at both of these assignments, and we take the better of these two assignments. That's our algorithm. Now, if we look at the expected performance of this algorithm, what we're going to achieve is the max of these two. So the performance, the expected performance of this best of two algorithm is the expectation of the max of M1 and M2. That's what our algorithm is going to achieve. And what we can prove is that this max is at least 3/4 the optimal value. Why is that? Well, that follows from the fact that each of these algorithms, the best of these two algorithms for each row on the previous slide, is at least 3/4. For every specific k, we get at least 3/4, and then we can analyze this in a clause-by-clause manner so that we get at least 3/4 of the optimal value. You can look at the online notes to see the calculus behind this. But the punchline is that this algorithm, this combined algorithm, gives a 3/4 approximation algorithm for max-sat, even when the formula has clauses of some small and some big. So even with formulas with varying length clauses, we achieve a 3/4 approximation algorithm.